The Coimbatore-based PSG and Sons Charities evolved a unique education and business model almost a century back. The four sons of the founder, Sri P.S. Govindaswamy Naidu, created a virtual fifth brother called Charity that has become the sprawling PSG empire, running not just several educational institutions but also manufacturing industries under the PSG umbrella. PSG and Sons Charities operates a state-of-the-art foundry at Neelambur, a suburb of Coimbatore. This 5-module video series, Inside a Modern Foundry, brings you various technical processes and specialized equipment that enable PSG Foundry to generate high-quality castings to meet customer demands across various industrial applications. In Module 1, an overview of the PSG business model was provided, along with the coverage of the pre-production foundry processes and pattern shop. Different types of patterns, pattern materials, and allowances that are provided were discussed. The dimensional aspects of patterns and the gauges and instruments used in pattern metrology were also presented.
In Module 2, 3 major topics are covered. The first topic is foundry sand processed at the state-of-the-art sand plant with details of composition, properties and testing parameters. This is followed by the second topic, core making at the core shop, covering the basic principles and need for cores and leading on to core sand, baking and core shooting. The third topic covered is molding using PSG Foundry's fully automated molding line.
In this module 3, 3 aspects relating to the most energy intensive operation of the foundry are covered. The first topic is melting, including its prerequisite furnace charge preparation, where the right mix of various ingredients is prepared for each charge loaded into the furnace. The second topic covered is pouring, where the molten metal is transferred to the molding line using conveyors and ladles. The third topic is the solidification of the poured casting along with its associated technical and metallurgical aspects.
This 5-module video series on PSG Foundry will be a virtual tour into a modern foundry explaining its intricate technical processes.
In a foundry, metals are cast into shapes by melting them into a liquid, pouring the molten metal into a mold, and removing the mold material after solidification of the molten metal. The sector-wise major consumer of castings is shown in this figure. The automobile sector is a major consumer of castings produced in the country. A recent survey by Indian foundrymen revealed that 68% of total castings produced in India are grey iron castings. Melting is the process of preparing molten metal for casting. After molding, melting is the major factor that controls the quality of the casting. Metals tend to have a higher melting point than many other materials, and they can change forms when exposed to heat. When temperatures become high enough, the ions that make up a metal vibrate more and more, eventually breaking the bonds and allowing them to move freely. When the internal structure of metal starts to shift and bonds are loosened, it becomes fluid. The strength of the bond based on the material determines the melting point of a metal. The melting temperature of various metals commonly melted in foundries is shown in this table. The melting temperature of grey cast iron is 1370 degrees Celsius. The melting temperature of cast steel is 1480 degrees Celsius. The melting temperature of non-ferrous metals such as copper and aluminum are 1083 degrees Celsius and 660 degrees Celsius respectively. The melting temperature of other metals such as zinc, lead and tin are 420 degrees Celsius, 327 degrees Celsius and 232 degrees Celsius respectively. PSG Foundry produces huge volumes of cast iron and spheroidal graphite or SG iron castings.
Cast iron is a group of iron-carbon alloys with a carbon content more than 2%. The various types of cast iron are grey cast iron, white cast iron, mottled iron, chilled cast iron, malleable iron and nodular cast iron, which is also known as ductile cast iron or spheroidal graphite cast iron.
Metals usually melt at very high temperatures, so the manufacture of cast metal significantly relies on furnace technologies. Heating furnaces of various kinds are used to heat the metal to a molten temperature sufficient for casting. The selection of the melting unit is one of the most important decisions foundries must make by considering several important factors such as the temperature required to melt the alloy, the melting rate and quantity of molten metal required, the economy of installation and operation, environmental and waste disposal requirements. The important furnaces used in foundries for melting are crucible furnace, cupola furnace, electric arc furnace, induction furnace, resistance furnace, rotary furnace and reverberatory furnace. Induction furnaces are used in PSG foundry for producing metal castings as per the customer requirements and production demands. The advantage of an induction furnace is that it is a clean, energy efficient and well controllable melting process compared to most other means of metal melting. Foundries take metal alloys and additives and melt them to make specific grades of cast metal. Every melt cycle starts with a charge. Melt cycle is the period when maximum power is continuously applied to the furnace and the charge is added. The charge consists of a suitable proportion of steel scrap of consistent quality, in-house returns, pig iron, machining chips, shredded mild steel scrap and runner and riser of knocked out castings. The charge materials are weighed using a rigid digital weighing unit before loading into the furnace. A suitable proportion of charge material is essential for ensuring the quality of the castings. The charge material is transported to the induction furnaces using magnetic overhead cranes. Mechanized charging systems are required for the charging of the induction furnaces. Inoculants such as ferrosilicon are added in liquid cast iron to provide good ductility and consistent characteristics in the final casting. They are used to control matrix structure and accelerate graphitization to avoid casting defects. Cast iron carbon is added to replace burnt out carbon during the melting of cast iron. The total carbon in the base iron should be 3.5 to 4% in spheroidal graphite iron. In the case of a higher percentage of carbon in molten metal, the quantity of sulfur, phosphorus and sponge iron in the charge is increased, and in the case of the lower content of carbon, the quantity of pig iron or cast iron in the charge is increased in suitable proportion. Sulfur, largely a contaminant when present, forms iron sulfide, which prevents the formation of graphite and increases hardness. The problem with sulfur is that it makes molten cast iron viscous, which causes defects. To counter the effects of sulfur, manganese is added. Because of the two forms into manganese sulfide instead of iron sulfide. The manganese sulfide is lighter than the melt, so it tends to float out of the melt and into the slag. Very low sulfur content also results in low nodule counts, poor graphite shape, increased shrinkage, poor machinability and brittleness.
In many instances, it is necessary to determine the content of carbon, silicon and sulfur to control the composition of metal. Carbon equivalent measurement is commonly used in gray iron, malleable iron and ductile iron. Carbon equivalent is given by this relation. Since silicon has a predominant effect on the graphitizing tendency of iron, the cumulative effect of carbon and silicon can indicate the strength characteristics of the iron.
Induction furnace capacities range from less than 1 kilogram to 100 tons. Induction furnaces are used to melt iron and steel, copper, aluminium and precious metals. The charging trough with a vibratory chute is used to convey the charged material to the induction furnace. Induction furnaces work with magnetic fields. Metal is charged into a refractory crucible surrounded by a powerful electromagnet made of coiled copper. When the induction furnace is turned on, the coil creates a rapidly reversing magnetic field by the introduction of an alternating current. As the metal melts, the electromagnet creates an eddy current within the molten metal that self-stirs the material. The heat in an induction furnace is created by the excitation of the molecules in the iron. There is no addition of oxygen or other gases to the system. To extract the maximum molten metal, a control mechanism is provided, which tilts the induction furnace to an angle of 90 degrees. The thermal efficiency of an induction furnace generally ranges from 58% to 76%. but in some cases where the power losses are minimum and a better control system is installed, the thermal efficiency can reach up to 80%. An advantage of induction heating is that the heat is generated within the charged materials rather than applied by burning fuel or other external heat sources. This is very important in applications where contamination is an issue. Since no arc or combustion is used, the temperature of the material is not higher than required to melt it. This can prevent the loss of valuable alloying elements.
The schematic cross-section diagram of an induction furnace is shown in this figure. The induction furnace consists of a crucible, inductor coil, shell, cooling system and tilting mechanism. The crucible is formed from refractory material.
A spectrometer is used to verify the chemical constituents of every metal melt before pouring to ensure the quality of the melt as per the Bureau of Indian Standards. After completing 50% charging of the input materials, a metal dab is produced using a sample of the molten material from the furnace. A hand ladle is used to take the bath sample. The metal dab is then placed in the spectrometer and it is vaporized with a testing probe. Arc spark optical emission spectroscopy is used to analyze the chemical constituents of the sample. The atoms and ions in the atomic vapor are excited into the emission of radiation. The radiation emitted is passed to the spectrometer optics through an optical fiber where it is dispersed into its spectral components. The radiation intensity is proportional to the concentration of the various elements in the sample. A breakdown of the chemical constituents by percentage is displayed on screen for analysis by the foundry engineers. If any elements are outside normal ranges, foundry engineers can finely tune the chemical constituents of the metal melt by further additions of the metallics as per the requirements. Temperature is one of the most critical process parameters that affect the quality, strength and working properties of a metal casting. Contactless optical pyrometer is used to monitor the temperature of molten metal continuously at various stages of the melting operation.
Foundry is an energy intensive industry. 70% of the energy is consumed during melting operation. Electricity is the only energy source for the induction furnace. The induction furnace circuit has a power supply frequency switching system. This system consists of a contactor combination for operating the main power circuit, a switchable resistor for reducing the surge current when switching on, which can be up to 6 times the nominal current, the balancing system with the load balancing reactor, capacitors and switching devices to control the system in line with the operating requirements, compensating capacitors with switching devices for controlled compensation, and the connecting leads to the furnace connection. The system is controlled using the devices in the operating cabinet. The induction furnace is to run at maximum power since the beginning of the melt cycle. Maximum power input increases the rate of melting and hence reduces cycle time. Depending on the material being melted, the capacity of the furnace and the melting speed, the operating frequencies of an induction furnace range from 50 Hz to 400 kHz and the power supply ranges from 10 kilowatts to 42 megawatts as per the requirements. Controlled current and frequency supply are needed for efficient melting. The power factor of the induction furnace is to be maintained near 1. As the power factor deviates from the unity, the quality of the system is said to deteriorate because of the harmonics and distortions arising out of power electronic devices such as rectifiers and inverters used in the power supply of an induction furnace. The power factor of the furnace tends to improve when the induction furnace is operated using 3-phase power supply. The power switching units incorporate heavy duty silicon controlled rectifiers that can generate both the frequency and the amperage needed for batch melting and can achieve a more than 97% electrical efficiency level. For effective heating in the furnace, the impedance matching network transforms the low current and high voltage of the inverter to high current and low voltage. The drop in voltage from the source also needs to be monitored for better energy efficiency. Further, the power consumption rate is dependent on furnace size. Power consumption is lowered as the furnace capacity is increased approximately up to 15 to 17 tons, and thereafter power consumption rate remains almost constant at around 620 kilowatt hour per ton of metal. The melting time can be calculated using available input power and power consumption. For example, if the available input power is 600 kilowatts and the power consumption for ingots is 550 kilowatt hour per ton, the melting time is calculated by dividing power consumption by input power. Thus, melting time equal to 550 by 600 into 1 hour, that is equal to 0.91 hour. In minutes, it is 54.6 minutes. Thus, it requires 54.6 minutes for melting 1 ton of ingots. Melting time varies from metal to metal. The operation of an induction furnace system requires a cooling water system. The cooling system is an induction furnace is a one-way flow system with the tubular copper coils connected to the water source through flexible hoses. The cooling process is important because the circuit of the furnace appears resistive and the real power is not only consumed in the charged material but also in the resistance of the coil. This coil loss as well as the loss of heat conducted from the charge through the refractory crucible requires the coil to be cooled with water as the cooling medium to prevent an undue temperature rise of the copper coils. In the furnace coil, the water is heated up to 62 degrees Celsius and must be cooled back down to 35 degrees Celsius. As per the requirements, 30 to 215 liters per minute of water must be pumped through the electrical equipment per kilowatt of performance loss. In the event of a power failure or other interruptions, an emergency water supply is installed for the furnace circuit.
Pouring is a process by which molten metal is transferred to the mold for cooling and solidification and thus converted into a final product. Once the melting is complete, the slag is skimmed off. The slag generated during melting tends to stick on the furnace walls. This reduces the volume of the furnace and hence reduces metal output per melt cycle. Superheating of metal is done at higher temperature and held for few minutes. This prevents slag from depositing on the furnace lining and keeps the furnace clean with full volume. At a temperature of around 1500 degrees Celsius, the metal reaches the desired specification. It is then poured into shank ladles or bull ladles for transfer to the pouring lines. The pouring rate refers to the volumetric rate at which the molten metal is poured into the mold. If the rate is too slow, the metal will chill and freeze before filling the cavity. If the pouring rate is excessive, turbulence can become a serious problem. The molten metal is also carried in a monorail ladle for transferring molten metal to a large number of molds waiting in the molding line. The ladle is mounted on the monorail for easy movement to the pouring site. A handwheel is provided for raising and lowering the crucible. At the pouring lines, molten metal is poured into the molds. Due to the lifting pressure of molten metal, molds will often be weighted or clamped to prevent them from separating at the cope and drag meeting point. Pouring temperature is the temperature to which the molten metal has to be raised before being poured into the molds for cooling and setting. The pouring temperatures for various metals are shown in this table. The pouring temperature is always kept higher than the melting temperature of the metals. The pouring temperature must take into account the heat loss caused due to the transfer of molten metal through ladles, as the distance between furnace and mold line has to be covered, and also due to the heat absorbed by the ladles. When molten metal is being poured into the mold at very fast rate, mold erosion, rough surface, excessive shrinkage may take place. When pouring rate is very low, the complete filling of the mold is not assured and may result in an excessive drop in the molten metal temperature. The soundness of the casting depends on how the metal enters and solidifies in a mold. From the ladle, the molten metal enters into the mold gating system. A good gating system is required to supply clean metal to the mold cavity, ensuring smooth, uniform and complete filling at a temperature and rate which will produce a casting free from defects. A typical gating system is shown in this figure. The gating system includes elements such as pouring basin or pouring cup, sprue base well, runner, and gates. Molten metal is carried in a ladle from the furnace to a pouring cup in the top part of the mold. Pouring cup establish a proper flow system as rapidly as possible and minimizes splash or turbulence. The sprue is the vertical passage through the cope that connects the pouring basin to runner or gate. The sprue well regulates, slow down and smoothens out the flow of molten metal to the runner. Runners are the channels that carry the molten metal from the sprue into the mold cavity or connect the sprue to the gate. Runner extension allows the molten metal to reduce the velocity due to an increase in the volume of the runner. The riser serves as a reservoir of molten metal to supply any molten metal necessary to prevent porosity due to shrinkage during solidification. Depending on location, riser is described as a top riser or a side riser. Gate is the passage that finally leads molten metal from the runner into the mold cavity. The term gating ratio is used to describe the relative cross-sectional areas of the components of a gating system. The dimensional characteristics of any gating system can be generally expressed in terms of the gating ratio A is to B is to C, where A is the cross-sectional area of the sprue, B is the total cross-sectional area of the runners, and C is the total cross-sectional area of in-gates. The gating ratios are grouped into two classes: pressurized gating system and unpressurized gating system. In pressurized gating system, gating ratios such as 1:2:1 and 2:1:1 produce a pressurized system. The total cross-sectional area decreases towards the mold cavity. Back pressure is maintained by the restrictions in the metal flow. The flow of liquid is almost equal from all gates. Back pressure helps in reducing the aspiration as the sprue always runs full. Because of the restrictions, the metal flows at high velocity, leading to more turbulence and chances of mold erosion. This system is generally used for ferrous metals. In unpressurized gating system, gating ratios such as 1:2:2 and 1:3:3 produce an unpressurized system. The total cross-sectional area increases towards the mold cavity. The restriction happens only at the bottom of the sprue. The flow of liquid is different from all the gates. Aspiration occurs in the gating system as the system never runs full. There is less turbulence in the system, and this system is generally adopted for metals such as aluminum and magnesium. Bernoulli's equation and the continuity equation are applied to establish a framework for analyzing molten metal flow through a mold. Bernoulli's theorem, which is based on the first law of thermodynamics, can be usefully applied to a proper understanding of flow of metal in a mold. Bernoulli's theorem can be expressed in the following equation. Bernoulli's theorem, which states that the sum of potential energy, velocity energy, the pressure energy and the frictional energy of a flowing liquid is equal to a constant. If this equation is divided by total weight of fluid flowing, all the terms have the dimensions of length and may be considered respectively to represent potential head, pressure head, velocity head and frictional loss of head. The potential energy of the metal can be considered a maximum as the metal enters the pouring cup or basin. This form of energy is then rapidly changed to kinetic energy and pressure energy as the metal passes through the mold system. Once flow is established and the potential and frictional heads are virtually constant, the velocity is high. While metal is flowing, there is a constant loss of energy in the form of fluid friction between the metal and mold wall. The law of mass continuity states that for incompressible liquids and in a system with impermeable walls, the rate of flow is constant. Q equal to A1 V1, that is equal to A2 V2, where Q is the volumetric rate of flow, A is the cross-sectional area of the liquid stream and V is the average velocity of the liquid in that cross-section.
Solidification. Solidification involves the transformation of the molten metal back into the solid state. The heat transfer during the complete cycle from pouring to solidification and cooling to room temperature is another important consideration in metal casting. Heat flow at different locations in the system is a complex phenomenon and depends on several factors relating to the material cast, mold and process parameters. Typical temperature distribution at the mold, liquid and metal interface is shown in this figure. The heat from the liquid metal is let off through the mold wall to the surrounding air. The temperature drops at the air and mold interface and mold metal interfaces are caused by the presence of boundary layers and imperfect contact at these interfaces. The shape of the curve depends on the thermal properties of the molten metal and the mold. The solidification process differs depending on the fact that whether the metal is pure metal or an alloy. The cooling curve for a pure metal during casting is shown in this figure. A pure metal solidifies at a constant temperature equal to its freezing point, which is the same as the melting point of the pure metal. The actual freezing takes time, which is called the local solidification time in casting, during which the metal's latent heat of fusion is released into the surrounding mold. The total solidification time is the time taken between pouring and complete solidification. After the casting is completely solidified, cooling continues at a rate indicated by the downward slope of the cooling curve. The characteristic gain structure in the casting of pure metal is shown in this figure. Due to the chilling action of the mold wall, a thin skin of solid metal is formed at the interface immediately after pouring. During solidification of pure metal, randomly oriented grains of small size appear near the mold wall and large columnar grains are oriented towards the center of the casting. Skin thickness increases to form a shell around the molten metal as solidification progresses. The rate of freezing depends on heat transfer into the mold as well as the thermal properties of the metal. The phase diagram for an alloy system and the cooling curve for a metal alloy during casting is shown in this figure. Most alloys freeze over a temperature range rather than at a single temperature. As temperature drops, freezing begins at the temperature indicated by the liquidus and completed when the solidus is reached. Owing to the temperature spread between the liquidus and the solidus, the nature of the dendritic growth is such that an advancing zone is formed in which both liquid and solid metal coexist. This solid liquid region is known as the mushy zone. If the solidus and liquidus are at the same temperature in an alloy system, that particular composition is called as eutectic alloy. The characteristic grain structure in an alloy casting shows the segregation of alloying components in the center of casting as shown in this figure. At the macroscopic level, the chemical composition varies throughout the entire alloy casting. Since the regions of the casting near the mold walls freeze first, they are richer in one component than the other. The remaining molten alloy is deprived of that component by the time freezing occurs at the interior. Thus, there is a general segregation through the cross section of the casting as shown in this figure. Once the molten metal is ready for pouring, a few standard metal specimens are cast and the specimens are subjected to microscopic analysis using a microscope with photography equipment and image analyzer to ensure the quality of the grain structure before pouring the molten metal into the molds for final production of the castings. Whether the casting is a pure metal or an alloy, solidification takes time. The total solidification time is the time required for the casting to solidify after pouring. Total solidification time depends on the size and shape of the casting by the relationship known as Chivarino's rule. Using Chivarino's rule, the total solidification time is calculated using the following relation, where TST is the total solidification time, V is the volume of the casting, A is the surface area of casting, N is an exponent usually taken as 2, and Cm is mold constant which depends on mold material, thermal properties of casting metal and pouring temperature relative to the melting point. Chivarino's rule states that a casting with a higher volume to surface area ratio cools and solidifies more slowly than one with a lower ratio. So, the riser is designed to have a larger volume to area ratio, solidifies first to minimize the effects of shrinkage.
When metals solidify and cool to form a casting, they generally undergo three distinct stages of volume contraction or shrinkage. The types of shrinkages are liquid shrinkage, solidification shrinkage, and solid shrinkage. During liquid shrinkage, the liquid metal loses volume as it gives up superheat and cools to its solidification temperature. During solidification shrinkage, the metal freezes, changing from a liquid to a higher density solid. For pure metals, this contraction will occur at a single temperature, but for alloys, it will take place over some temperature range or freezing interval. During solid shrinkage, the solid casting cools from its solidification temperature to room temperature. The solid shrinkage, also called as pattern maker shrinkage, is accommodated by making the pattern somewhat larger than the desired dimensions of the final casting. Liquid shrinkage and solidification shrinkage are the concern of risering practice. A riser is added to accommodate the liquid shrinkage and to supply liquid feed metal to compensate for the solidification shrinkage within the casting.
To minimize damaging effects of shrinkage, it is desirable for regions of the castings to be in far off distance from the liquid metal supply to freeze first and for solidification to progress from these remote regions towards the risers. This is known as directional solidification. Desired directional solidification is achieved using Chivarino's rule. If the solidification starts at the walls of the casting and progresses perpendicularly, it is known as progressive or parallel solidification. A shrinkage defect will be there when progressive solidification dominates the directional solidification. Internal and external chills are used to promote solidification when a heavy section of casting is remote from the source of feed metal or when it is difficult to mold a riser in the required place. Chills are metal shapes used to speed up the solidification in heavy sections, thus permitting the shrinkage that takes place to be fed through adjoining sections.
Fluidity is an important characteristic of molten metals and alloys, and it directly affects the casting soundness and metallurgical quality. Fluidity is the capacity of molten metal to flow within a flow channel or inside the mold over a defined distance. The most common fluidity test used in foundries is the spiral fluidity test. A few samples of spiral fluidity test are shown in this figure. In this method, the liquid metal is poured in a mold forming a long thin spiral, and the length into which the metal is able to run is taken as a measure of fluidity. Grey cast iron is the most fluid of all the ferrous alloys.
Once the molten metal is poured into the mold is allowed to cool for approximately 30 minutes before it is taken to the shakeout. Poured molds are then dumped into a vibrating conveyor wherein they are broken up by the vibration, exposing the casting for removal. Finally, the sand from the mold separated and processed through a reclamation system. The reclaimed sand is mixed with pure sand in the ratio of 80% reclaimed sand and 20% pure sand for further use.
In this module, the third of the 5-module series inside a modern foundry, 3 important PSG foundry processes have been covered. Charge preparation prior to melting refers to preparation of the right combination of various ingredients in the right proportion. Charge preparation precedes the actual melting, and stringent and scientific control measures are adopted at PSG Foundry to ensure the right composition and proportions of various charge materials used. Once the charge is prepared, the furnace is loaded and the charge is melted into molten liquid form by heating it to the stipulated temperature and cycle time. The operating principles of the energy efficient induction furnaces are explained, as well as the thermal and metallurgical characteristics during the heating cycle. As the melting process constitutes the most power intensive part of the foundry's operations, the powerhouse at PSG Foundry with its sophisticated power control and monitoring equipment has also been covered. The molten metal is then transported to the molding line where already assembled mold boxes are ready to receive the molten metal in an operation called pouring. Here again, it is important to ensure close monitoring and control of different process variables. Post pouring, metallurgical and intricate technical aspects of solidification of the casting are covered. Throughout this module 3, various intricate equations and models are used to supplement the visual content with graphs and charts. The 3 topics of melting, including charge preparation, pouring and solidification, have a significant impact on the overall quality of the final casting.
Thank you.